I know we're all here to learn about the eclipse. We're very excited for tomorrow's happening. So I will introduce our speaker. Jonathan Rebelsky is an analytical chemistry PhD candidate in the Department of Chemistry. Jonathan earned a bachelor's of arts in of music from Grinnell College in music and chemistry and works in the Widicus Weaver lab studying prebiotic ions and radicals in the interstellar medium. So please give a warm welcome to Jonathan.
Thank you so much. Today I'm going to talk to you about when the sky turns dark, understanding how, when, and why eclipses happen. We've got here a beautiful sort of time-lapse image, what happened at the last total eclipse back in 2017. We can see some cool parts, you know. Is this the... Sorry, just trying to figure out where the laser... Oh, well. Right, you know, we can see the moon starts to go in front of the sun, nothing too exciting. But as we get to totality, we end up seeing the corona, you know, that beautiful white bright thing across the sun. So I know some of you are only here because you didn't know that there was an eclipse tomorrow and would like to know exactly when it is. If so, there's a total solar eclipse tomorrow, very exciting. Here in La Crosse, it will not be totality, but it'll be about 84%. So the moon will start intersecting the sun at 12:49 p.m. La Crosse time. It'll peak at 2:04 p.m. at 0.842 magnitude. So, you know, that magnitude goes from 0 to 1, 0 being just the sun, 1 being just the moon. So right, it covers most of the moon, most of the sun, and it'll end at 3:17 p.m. You know, that's when the moon will completely leave the sun again. Eclipses always come in pairs. That's just a fun thing to know. And so we just had a penumbral lunar eclipse on March 24th, 25th. It started at 11:53, peaked at a magnitude of negative 0.13. You might be asking, how do you have a negative magnitude? I thought it went from 0 to 1. You get negative magnitudes when you have penumbral eclipses. What are penumbral eclipses? Great question. We'll talk about that later. One thing you might notice, right, is solar eclipses last less long than lunar eclipses, right? The lunar eclipse lasted about 4.5 hours. Solar eclipse only lasts for about 2.5 hours. There's reasons for that as well. So, you know, if you want to go down to totality, I would have recommended making plans a couple months ago. But if you want to make plans today, here's the path it'll take. You know, it'll trace through most of the country. Obviously, the closer to the middle line you are, you can see there's that faint interior line in the middle of the strip. Closer to that you are, longer you'll see totality. There's a region in Mexico where the longest amount of totality will happen at about 7.5 minutes. That's really exciting. This is also the last total solar eclipse that will be in the United States until 2044. All of those modifiers are necessary. I think there is a total eclipse in Cairo in like 5 or 6 years. So now that we've gotten the formalities out of the way, right? Like, what are eclipses? Or not what are eclipses, when is this upcoming eclipse? We can talk about the general case. So before we talk about the general case of eclipses, I'm getting my PhD in chemistry, so I obviously think science is important. If you're unaware, the University of Wisconsin-Madison has this thing of the Wisconsin idea, which suggests that the university's impact shouldn't end at the gates of the university, right? It should extend to the whole state of Wisconsin. That's why the Badger Talk program exists. And so part of that for me is, right, like, it's important to me not just to be like, this is how eclipses work, but also to do the broader impact of like, who cares? So, you know, there's this idea I heard a lot as a music student. I've heard a lot in my life, like science and wonder are sort of at odds with each other, right? When you have scientific explanations for things, it's not exciting anymore, right? Oh, you can explain it away. But really, science is about the opposite, right? It's that childlike wonder of asking why, and then when you get an answer, asking why again. Parents of small children, I'm sure that's something you're used to. You know, they're like, "Why is this?" And you say, "Oh, because, you know, like, why is the sky blue? Oh, because air is blue. Why is air blue? Well, what's blue? You know." And so, really, the better at science we get as a culture, society, body of knowledge, the more why questions we can ask, right? If we think about ancient times, Why is there lightning? Oh, some lightning god is mad and throwing lightning bolts. You can maybe ask like, why is he mad? But that's as far as you can go. Nowadays we can go like, why do we have a lightning storm? Oh, there's a charge imbalance somewhere in the cloud. You say, well, how do we have a charge imbalance, right? And we can keep going and keep going. Now, of course, my degree's in chemistry, so I think of the world as chemicals, right? The way I view the world is fundamentally shaped by my discipline. So to continue this sort of, what are the broader impacts? What do you mean by why? We're going to talk about what's chemistry made of. Chemistry is made of matter. What's matter? Great question. We can, eclipses, we tend to think of, same way we think of the night sky, very much in terms of how the ancient Greeks thought of it, right? The constellations we use are the same ones they had. Ancient Greeks generally, and actually most of the ancient world as far as records exist, suggested that the world is made of four things. You got fire, you got water, you got earth, and you got air. As an example, you can think of wood, right? We can dry wood out, so we know there's some water in wood. You can light wood on fire. That releases the fire inside of the wood under this model. And then when you burn wood, you've got some ash. So look, there was some earth in there too. And this works kind of to explain how things work, right? You can say, what's wood made of? Wood's made of some fire, some earth, and some water. But what's fire made of, right? That's this great question. There's not really an answer for it. There was still this idea, right, of like, can we separate matter into infinitely small chunks? Big area of debate for millions of years, thousands of years probably. And so yes was the general consensus, right? There was this tiny indivisible particle called an atom. What are atoms made of, right? For the longest time we thought fire, water, earth, air. Isaac Watts shows us that's not true, right? We have elements. We've got 118 now, potentially more. Stay tuned to your local high energy physics lab. But right, this is what everything we know is made of. But even atoms aren't really what we see most of the time, right? We tend to see large collections of things. In 1 ounce of water, right, you've got 10 to the 24th molecules of water. It's a lot of things, right? It doesn't really make sense to talk about one hydrogen atom in any of our lived experience. So right, these are all atoms because you can't break them. You can, if you've seen the movie Oppenheimer, you know exactly how you can break an atom. But it turns out atoms are not the smallest building block of reality, right? We say like, what's water made of? Water is made of water molecules. What are water molecules made of? Hydrogen. What's hydrogen made of? Turns out hydrogen has a proton and electron. Those are not the most fundamental particles, right? Your proton is made up of, on average, 3 quarks, 2 up and a down. What are quarks? Great question. I'm not a particle physicist. I know they exist, and that's about where I stop caring about them. But also, quarks get back to this really weird thing in science, which is things can exist in a very meaningful way, and things can affect us in a very meaningful way without really being able to be observed, right? An individual quark doesn't exist in any meaningful sense, and yet it still has impacts on our life. It's fun, right? We look at the ancient Greeks and we're like, wow, they thought the stars controlled their lives. Isn't that ridiculous? But then we go, right, these quarks, which we know, you can't just observe a quark. It doesn't exist. That also is what we're made of. And so this, ancient Greek idea, ancient classical idea of as above, so below, we see throughout most of pre-modern history. How do you treat an ear infection? You find a plant that looks like an ear. There's something to it. Okay. Now that we've talked about what everything's made of, let's go from small scale to big scale, right? Done with our microscopes, bring out the telescopes. So what is an eclipse? Technically, there's a lot of definitions. As with any word, depends on the use case, right? We're in a library. I'm sure many of us are familiar with that hit 2010 book series about vampires, third book of which was Eclipse. Maybe not the right crowd for that joke. But, right, this is a talk primarily about astronomy. So we're going to focus on the astronomical definition, which is any time 2 heavenly bodies intersect. Of course, that's already not a fantastic definition, right? Like the moon tracks across the sky every day. The sun tracks across the sky every day. Technically, every time it intersects, they go over a different star. That's an eclipse. But, obviously that's not what we're talking about. We're not here to see the moon go in front of some random star. We're here to see something like this beautiful solar eclipse. So we tend to think of the two kinds of eclipses being solar eclipses and lunar eclipses. But, solar eclipse when we can't see the sun. Are there any other times we can't see the sun? This is an audience participation question. Nighttime, right? So a question we could ask ourselves, are eclipses related to days, right? We've got this idea of a universal harmony, cycles within cycles. Turns out you can predict eclipses. They do happen in a periodic motion. So do they happen every day? In a sense, yes, right? The Earth gets in the way of the sun every day. It becomes night. Also, kind of obviously, you can only have a solar eclipse during the daytime because if it's night, you wouldn't see the moon in front of it. Right, like it feels obvious, but it's also an important truth. A little more interestingly, you can only have a lunar eclipse during the night, which does make some sense, but also feels a little weird. Why does it have to be nighttime? Of course, right, a day alone is not enough to explain how eclipses happen, right? They're not a daily occurrence. So we can go up. What's the next biggest unit of time we tend to care about? Like a month, right? What is a month but one cycle of the moon? So do eclipses have to do anything with phases of the moon? Yes. Generally, when I ask a question in this talk, the answer is going to be yes. Solar eclipses can only happen at new moons, and lunar eclipses can only happen at full moons. That's pretty interesting. We know that the moon cycle is 28 and change days. So maybe our question is, okay, we've got these two cycles now, right? A day and a month. If we add those two cycles together, is it every time they overlap that we get an eclipse? No. What's bigger than a month? Allegedly, right, seasons nominally exist. Given the snow last week, questionable in Wisconsin. As it turns out, eclipses kind of are related to seasons, not in the most useful of way. We have an eclipse season about every 5 months. Every eclipse season, there's one solar and one lunar eclipse. They always come in pairs. They come 2 times a year, except for those lucky years where we get 3. And with these 3 things, we kind of get enough to explain stuff. But right, I've just been throwing a whole bunch of scientific words at you, like what is a day? What's a year? And so it's good to like take a step back and think about it. So we've got the entire universe here, right? You've got a planet and the sun. We'll call this planet Earth. There are other things, of course. We don't care about them, right? They don't affect the eclipse. So, right, a day is the time it takes the Earth to spin all the way around. We can see we've got the blue blue side, red side. Sometimes the blue side's in the sunshine, sometimes the red side's in the sunshine. And that feels easy enough, right? Like, this is an intuitive way to think of a day. Assuming we believe in heliocentrism, which if you don't believe that the sun's at the center of the solar system, I'm really sorry to break it to you. It is. Right, so day, very easy to understand. Time it takes the Earth to spin around itself. Next easiest thing to understand is a year, right? A year, also pretty simple. Time it takes the Earth to go all the way around the sun. Weird thing about a year, right? A year is not an integer number of days. Integer means, right, like a whole number. We can see, right, we go all the way around, and the Earth's turned about a quarter of the way there, right? At the start of the year, blue side was facing. Now we're halfway between blue and red. If we want to be precise, right, it's like a little under 0.25, it's like 0.246. That's why this year's a leap year, but 2100 will not be a leap year, but 2000 was a leap year. There's a whole bunch of math about it. And that can feel weird, right? Like, why isn't the year an exact number of days? And then you can take that step back and be like, there's no reason that how fast the Earth spins around its own axis would be related to the amount of time that the Earth spins around the year. Right? They are completely independent of each other. And suddenly it becomes kind of weird that 365 and a quarter works so well as an approximation. So, it's one of those weird things where it works, but it doesn't work, and we kind of just have to deal with that. So, right, obviously we care about things between years and days. We talked about a month. Month most easily defined as a lunar month, right? The amount of time it takes the moon to go around the Earth. An interesting thing we can see, right? The moon is tidally locked to the Earth. We can only ever see one side of the moon. In this model, that's depicted by the fact that the blue side is always facing the Earth. Some of you might have heard of the dark side of the moon, right? India just landed a probe there. We can see from this picture that, right, like every part of the moon gets just as much sunlight. It's just when the red side of the moon is getting sunlight, it's not shining on Earth. And so this is like a really nice, helpful model to understand a month. And like many really helpful, simple models, it's fundamentally wrong, right? We've been saying it's the amount of time it takes the moon to go back to its starting place, new moon to new moon. But the Earth's moving at the same speed, at the same time, right? And so what we really have is a month that looks something like this, right? As the moon's orbiting the Earth's moving. And so this gives us two different ways of defining a month, right? We can do the time it takes the moon to go horizontal compared to the Earth, right? Here we're looking down at the solar system. We can imagine, right, the stars basically stay in the same place because they're so far away. So if we compare where the moon is to where the stars are, we get one definition of the month. We get the sidereal month, Greek for stars. Or we can think about new moon to new moon, right? This little added bit at the end, a synodic month. So that's sort of the easier one to measure, right? You can go full moon. That'll be 28 1/3 days. It's about a day less to have your sidereal month. And as it turns out, those 3 cycles are almost everything we need to understand how eclipses work. So before we go into like what eclipses look like, let's define more words. One thing you'll learn, especially children in the room, the more you learn science, the more it's just learning a bunch of words and then finding out that what the words refer to is really cool. So lunar eclipses, right? We just had a penumbral lunar eclipse. As we said, right, there's only 3 things in the solar system that matter: the Earth, the sun, and the moon. Right, the sun's really big, but it's also really far away. The Earth's really big and we're on it. The moon's really big and kind of far away. So we can imagine, right, if you had a really big bright thing and you put a dark thing in front of it, you'll see that its shadow kind of breaks into 3 pieces, right? You've got the region called the umbra, where you can't see any of the sun, right? You know, if I'm standing behind that pillar, there are parts I can't see. Other parts, right, as I'm further away or as I'm to the side, you can see different things, right? You know, hold your hand up in front of you. Depending on where you put your hand, you can or can't see the projector. So it's a penumbral lunar eclipse because the moon was in the penumbra, not the umbra. So a lunar eclipse, right, we've got the Earth between the moon and the sun. So what's a solar eclipse? You might think, as many of my group mates did when I asked them this question, if a lunar eclipse is when the Earth is between the sun and the moon, then a solar eclipse should be when the sun's between the Earth and the moon. And that feels intuitively right. It's wrong. I want to be very clear, right? The moon is always closer to us than the sun. That's how we're still alive. So solar eclipse, the moon gets between the Earth and the sun. And right, we can kind of see why that would make sense as these come in cycles, right? Moon's on one side, gets to the other side, gets in front. The moon is a lot smaller than the Earth, so it's kind of hard to fit words on here, so we'll zoom in real quick. Right, once again, we've got that penumbra, umbra thing with the moon. Of course, right, the moon is a lot smaller than the Earth and a lot smaller than the sun. And so the region where you're in total darkness is much smaller, right? I didn't give a map of the most recent penumbral lunar eclipse because it was the entirety of North America could see the penumbral lunar eclipse more or less identically. Whereas with this lunar eclipse, right, we're in the penumbra, sure, but that's much less exciting. Some of you might know that back in October, we had an annular solar eclipse. What's an annular solar eclipse? So sometimes the moon's at different distances relative to the Earth, and the Earth's at different distances relative to the sun. And right, the same object, closer or further away, will look larger or smaller. So same moon, a little bit further away in this example. We now have what's known as the antumbra, right? So, you know, if I hold my hand up, it is completely blocking my face from you all. But you can still see my face because it's smaller on it's just smaller, right? So in the Antumbra, the moon is entirely in front of the sun, but the sun still has still peeks out from behind it. Cool. So now that we know what eclipses are, we know all the fancy words, let's look at them. So what do we see from Earth, right? Here we imagine we're standing on Earth and we're perfectly tracking the moon, right? We know over the course of the month, the moon gets closer and closer to a new moon. In this case, we had an eclipse, right? It's really pretty. These are simplified models, so we will get total and total. So right, we know that as the moon continues to go, it waxes and waxes and gets bigger and bigger. And then in times when we'd have a lunar eclipse, right, just before the full moon, it'll get covered. In real life, you'll notice that the moon actually gets kind of red. The same reason that sunsets are red is the reason that the moon turns red during a lunar eclipse. There are many ways to explain that. The easiest one is the sky is kind of red and kind of blue. The more complicated way is Rayleigh scattering. The intermediate explanation, red light gets blocked less. So right, moon goes, at the full moon, it gets blocked. At the new moon, it blocks the sun. We can contrast that, right? Most of the time, that's not what happens, right? We have the new moon, the moon continues to rise, crests, half moon, 3/4 moon, all the way to the full moon, right? And there's no eclipse. And these look more or less the same, right? The path of the moon looked the same. If you looked, it's kind of hard to figure out what the difference was. So what's the difference, right? That's a very big question we can ask ourselves, right? We can continue to let this movie play as long as we want, but I promise we never get an eclipse in this movie. So this is where we learn the really fun thing of graphs can lie to us, right? The way you present your data can affect what you get from the data. So we've now got a slightly more complicated image. So we've got 3 views of the solar system, right? We've got on the left sort of a side-on view. So imagine the Earth and the Sun are here. We're looking side-on. We've got a top-down view, right? What we'd see if we were looking from above. And then we've still got our view from the Earth. So this is where I reveal that I've been lying to you this whole time, right? The moon does not orbit the Earth in plane with the sun. It orbits at about a 15-degree tilt. And so, as makes sense, right? It intersects the same plane as the Earth and the sun twice every orbit. And so when we don't have an eclipse, places where it crosses through the plane are not places where it's between the Earth and the sun, right? We see the lunar eclipse here can't happen because it's below the Earth. In contrast, right, when we have the eclipses, it intersects the plane when it's coming down there. And in this case, right, like the side-on and head-on look a lot more similar. And one thing I said, right, is lunar eclipses much more readily visible than solar eclipses. And so we can see an example of that, right? We don't have a solar eclipse in this month, but we do end up with a partial lunar eclipse. So that's all good and exciting, right? So the reason we have eclipses is that the moon orbits the Earth and sometimes intersects the plane between the Earth and the sun. The reason we don't always have eclipses is that this 15-degree angle stays constant as the Earth goes around the sun. And so sometimes the full moon gets in plane and sometimes the full moon doesn't. So we can return to our idea of science and wonder. So right, we now know how eclipses work. So if we were one of those people who says science is about killing mystery, right? It's done. The fact that the sky gets dark isn't exciting, right? That's what happens when you block the sun. But we don't want to do that, right? We want to look for the joy in things, right? So one question we can ask ourselves, what have scientists discovered from eclipses? One thing we've discovered, right? The corona exists. The sun is not just a ball of fire. It has this wide emission. We discovered helium in the corona of the sun. So if you take light, right, you can shine it through a prism. We've all seen those album covers where you get white light turns into a rainbow. We've all seen rainbows. And if you do this really carefully, one thing you notice when you look at stellar emission from the corona is that there are these really sharp features missing. And some of them we found, right? If you apply electricity to water, you can break it into hydrogen and oxygen. And then if you shine light on hydrogen, it absorbs at really specific colors of light. And so scientists did that and they're like, oh, hey, there's hydrogen in the sun. That makes sense. And then they found these unknown lines they couldn't assign to anything we'd seen on Earth. And so they said, well, it's in the star. Greek word for star is helios. So it's star stuff, helium. We eventually find it on Earth. It matches up because sometimes science works. Another thing, right, there's this misconception a lot of people have that Christopher Columbus discovered the Earth was round. We've known the Earth was round, we being like, it was known, not every single person everywhere, since around 300, at least in the West, right? Most things when we talk about was known by people are from the Greeks to the Romans, to the descendants of the Romans in Europe. Every culture has their own knowledge base. They are not always overlapping. Feels like a very important disclaimer I need to make more often. But right, so the Greeks knew that the Earth was round because when you look at the shadow on a lunar eclipse, it's always a circle. And the only way you can always have a circular shadow is if you have a sphere, right? If you imagine shining light onto a cylinder, as you change the direction of the light, it changes shape. And then, right, like eclipses are kind of wonderful and mysterious. And quick show of hands, who knew that the eclipse was tomorrow before you came to this talk? Keep your hand raised if you knew the eclipse was April 8th, a year ago. Keep your hand up if you knew 10 years ago. Right? Fun fact, you can go to the NASA webpage and get eclipses predicted all the way out to 2500. That's just because that's where they stopped predicting it, not that we can't predict past that, right? And this isn't a new thing people can do, right? There was this fear back in 2012 that the world was ending because the Aztec calendar ended. Do people remember that? Okay, yeah. So right, the calendar ended in the same way that our calendars end because they got bored of adding more time and said, we'll make a new one later. Events happened, they didn't end up making a new one. But one really cool thing about that, right, is the calendar lasted about 600 years, and in that 600-year period, they predicted all of the upcoming eclipses. This is not like a thing that only the Aztecs did. More or less, when you look, any culture that has written records has predictions for when eclipses happen. And it makes, if you've ever seen a total eclipse, either solar or lunar, it makes sense why you would want to be able to predict them. It is very scary to be standing outside and then suddenly the sun goes dark. If you don't know that it's happening, it's very reasonable to feel like the world's ending. Even knowing what was happening back in 2017 at the last eclipse, I was still like, oh, what if the sun doesn't come back? Like it was a thought that went through my mind that I could not get rid of until the totality ended. And so, right, it becomes very, people have always been superstitious. People are still superstitious. It is very valuable to know when something that feels important is happening. Yes. Great. So, eclipses, science. What are questions we can ask about eclipses? We in this room, thought experiments, not science experiments. What if the moon was closer or further, right? Things can orbit at any distance. The moon is steadily getting further away from us. Any guesses what would happen if the moon was closer to us or further from us? Aside from like tidal effect and the moon would look bigger in the sky and all of those other, not eclipse related phenomena. Yeah, closer goes around faster, further goes around slower. Right, yeah, we talked about how annular eclipses happen because the moon's orbit isn't perfectly circular. Sometimes far enough away it doesn't cover the sun entirely. And right, if the moon was further away, we'd see more and more annular eclipses, which, it's cool, but it's nowhere near as cool as that total eclipse, right? If the moon was closer, takes up more of the sky, could cover more of the sun, we would see more and more total eclipses. If the moon was too close, though, right, it would also not be exciting because it could also cover the entirety of the corona. I mean, it would still be dark during daytime, so that would still be exciting. Another question we can ask, right? The moon's inclination is about 15 degrees. What if the moon had a different inclination, right? We can imagine the moon's inclination being perfectly in plane with the Earth, in which case every full moon becomes a lunar eclipse and every new moon becomes a solar eclipse. And now we get to the not science, but wonder part. Right, like the eclipse is really cool. The last eclipse, businesses estimated a loss of $8 billion of productivity. Not that I believe we should measure like things and how much time people spent on them, but right, a lot of people took time off to see the last eclipse. I think that was a good thing generally. I think we should go explore things, find more wonder in our life day to day normally. But right, people made a big effort to go see the last eclipse. People are making huge efforts to see this eclipse. Show of hands, who's made an effort to see the last full moon? Right, you know, some of us, but not many. Who makes a daily concerted effort to like watch the sunrise and sunset? Right, but like those are beautiful too, right? They're really cool. If you didn't know what was happening, they'd feel mysterious. So there's this thing where, right, if the moon's inclination was perfectly flat, eclipses becoming more common might make them less exciting. We can imagine other scenarios, right? If the Earth orbited differently, had a different spin rate, eclipses would happen at different places and different times. If the inclination was different and the orbit was different, right? We can conceive of a place where the moon never crosses that same plane at the new moon or the full moon. So right, there's infinite questions you can ask. And the cool thing about science is you get to ask them. And then you can go through and do a bunch of math and go, oh, this is what would happen. And then often you can run an experiment. If you said, dear funding agency, I would really like to change the inclination of the moon to see what it does to eclipses, they would not give you the money for that for many reasons. But a lot of things you can say, what would happen if, and then try it, right? I can go, what happens if I apply 800 volts to a gaseous mixture of nitrogen and hydrogen? And the answer is you make a really unstable molecule, but you make it stable. That's an experiment I'm working on right now. So, right, what if days longer or shorter? If the day is longer, it becomes easier and harder to see a solar eclipse, right? Solar eclipses only happen in daytime. Again, some of you were here to find out about the eclipses. It is tomorrow. It begins at 12:49. It ends at 3:17. If you're standing here, if you're elsewhere, it'll start and end at different times. I have been told that as a spokesperson for eclipses, it's important for me to tell you about eclipse safety. Don't stare at the sun. It feels like obvious advice. It is obvious advice, right? Day to day, you know, this is a question for the people under the age of 18 in the room. Have you ever been told not to look at the sun? Give me a show of hands. Great, right? You know, we've been told not to stare at the sun, and that's good advice. If you've been told not to stare at the sun, don't. But if, like me, you ignored things that you were told and you looked at the sun, right? It hurts to stare at the sun. Right, yes, okay, good, I'm seeing nods. So that's this really cool thing where most of your body has pain receptors to tell you when you're doing something which hurts it, right? If you touch a hot stove, you go, ow, that hurts, and you take your hand off, hopefully before you've done much damage. The issue with the sun, right, is visible light doesn't really harm your eyes at all. It's the ultraviolet light that really, and the X-ray light, and all of the like high energy light from the sun that hurts you. Your eye, right, as we can tell by calling it visible light, is most sensitive to light in the frequencies we can see, right? I can't see infrared light because it's definitionally infrared, but also, right, like my eye has areas it can see. And so those are also the areas that the pain receptors are tuned to. During a lunar eclipse, during a solar eclipse, right, it gets darker, you can see less sunshine, there's less visible light. The amount of UV light isn't significantly different. So, right, if you normally stare at the sun for 30 seconds a day, I would recommend stopping that habit. But, right, like if you know how long you can stare at the sun on a typical day without pain, it is no more dangerous to look at the sun for that amount of time during an eclipse. It's maybe, 3% safer. The issue is, right, if you normally stare at the sun for 30 seconds before it hurts, during an eclipse, you'll be able to stare for like 5 minutes. that is much more radiation that's really bad for you. If any of you have like tried looking through the eclipse classes, you might notice you see basically nothing. The sun is really bright. Quick show of hands, who has experience with welding? Or like, has heard of it, I guess. Right, welding masks, when you do an arc weld, you make really bright light, and that requires really special equipment so you don't blind yourself. Arc welding equipment is not sufficient to block sunlight because the sun is really, really bright. So yeah, that's really all I had. Any questions? Yes. Oh, there's a microphone.
In 2017, what was the percentage of the eclipse here?
Yeah, so the question is in 2017, what was the percent coverage here? I don't have that number off the top of my head. I think 70 to 80%, if I had to guess. I think so, yeah. Yeah, I think this one's a little better if I like remember the paths right. There was another, yeah. Yeah, so it depends, right? Here, lots of visible light, also lots of UV. Here, not much visible, but still a fair amount of UV. Technically, during peak totality, if it's actually totality, it is safe to look at it. The issue is, right, the difference between 100 and 99 is the difference between the UV light being blocked and not being blocked, but it's hard to tell visually. Yeah. 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 The question is, how often are eclipses around the world? So there is a type of solar eclipse every 5 months, whether that's a partial eclipse, an annular eclipse, or a total eclipse. Total eclipses, on average, every 3 to 5 years, is sort of the like when I looked last. So right, they're not super rare. They're just fairly rare in any given location. And also the Earth is primarily water. So that's the other thing is, right, most eclipses no one gets to see because they're entirely over like the Pacific, and no one is going to go chart a very precise location in the Pacific. That's not true. I can't say no one. Very few people would. Yeah. To clarify, yeah. So to clarify, your question is, what's the relationship between the auroras and eclipses? Is there a relationship? Yeah, so the aurora would look the same as it tends to look, because right, it is functionally nighttime when an eclipse, total eclipse happens. So if you are somewhere in a northern latitude high enough for the aurora to be visible that night, also in path of totality, you would see the aurora as totality happens. There was, oh yeah.
So if you could imagine like a round object on a surface.
Mm-hmm.
Bam, bam. Last week was both US.
Yeah.
This way, crossing that way, and then as it other way, so it sort of follows that same spherical disk.
Yeah, so the question is, right, we can imagine the Earth rotating as sort of like a ball rolling around a table. So no, right, if we go back many, many slides, when we talk about a year, right, the Earth changes orbit about a quarter rotation per year. And so as it turns out, right, the eclipse happens about the same time every year, happens about a quarter of the Earth further. And so it's just that there's, let me remember, I think it's 19 solar years is when you get a repeat of all of your same lunar patterns. So every 19 years, we see the same eclipse in allegedly the same position, but right, 19 does not get us back to a perfect day. And so every 19 years, we see the same eclipse shifted on the Earth slightly. It's just that there's different eclipse paths. Yeah, so like the total eclipse we saw in 2017, that exact same eclipse will happen in another like 12 years. It'll just be over the Atlantic this time because the Earth is more rotated. Cool. There was, yeah.
Bit off, but I had heard on a radio discussion about the effect of solar eclipses on power grids. Know anything about that?
Yeah, so the question is solar eclipses and power grids. There's the obvious one, right, of like a bunch of people will be in an area that there aren't normally a bunch of people. That adds more tax to all the grids. Other than that, I don't know of any direct effects.
Of the lack of income, and then a sudden incoming might disrupt.
Oh, for like solar grids?
Yes.
Yeah. Yes, I could see an issue, but again, right, an eclipse, while very interesting and rare, is not significantly different than like very heavy cloud cover localized. So I would imagine that solar panels can handle it. As somebody who doesn't work with solar panels, I can't guarantee that though. You had a question? Yep.
Does eclipse only refer to sun, the moon, and Earth? Can there be eclipses of like
Yeah. So yes, technically right. Every time the moon gets in front of a star, that's an eclipse. Because it happens so often, we don't really care about them. When two planets in the solar system are interrupting each other, astronomers do get excited because then you have like an eclipse of Mars by Jupiter, Jupiter by Mars. Right, it looks like, hey, you had two stars, now you have one star for a second, then you have two stars again. So it's much less exciting to the amateur viewer. But yes, technically anytime objects overlap each other, it becomes an eclipse. Yeah.
I think I understood you earlier to say that there's evidence of people seeing and understanding eclipses due to calendars.
Mhm.
Are you aware of any other cultural evidence, like something like cave drawings or other kinds of evidence that shows that people had an awareness and interest in eclipses?
Yeah. Oh, so the world of paleoarchaeology or paleoastronomy, so like ancient, cave drawing era people and their astronomy is incredibly contentious. There are many people who claim that Stonehenge was built for some astronomical purpose because it lines up every solstice. And there are many people who have written thousands of pages on both sides of that argument. So going back that far, we don't have any good evidence because we don't have any strong evidence of any cultural practices then. But we do have like Babylonians have writings on it. The Chinese have writings on it. The Mayans had, or either the Mayans or the Aztecs, I'm forgetting now, had the calendar. So yes, more or less every culture that has writings about eclipses. And most of those cultures, to my knowledge, also at least one group of them had a way of tracking the eclipses. Generally some sort of a priestly caste. We can talk about why the correlation between the religious elite and the educated was more or less one-to-one until the modern times, but that is not maybe for this talk.
Paleoastronomy?
Yep. Or archaeoastronomy, depending on, yeah. But yes, there's a lot of contention. There's a lot of really cool hypotheses that we, of course, can't test. Yeah, question in the back? Yeah, yeah, so there's of course this like, at what level do we want to explain it? I'm gonna go for the easiest level. So my shirt is white with blue stripes, right? I don't know, that wall is blue. Why is that wall blue? That wall is blue because it absorbs all the light hitting it that isn't blue, and it reflects the light that is blue. So then you get that fun question of what color is something in darkness? And there's an equally reasonable answer to say, when there's no light, everything is black. And when there's no light, things are the same color, right? Because it's that question of what is color? Is color the observation or is color the intrinsic property? Anyways, nitrogen absorbs light that isn't red. So when you have more nitrogen in the sky, it absorbs more of the non-red light. The sky becomes redder. Yeah.
The other day that if you're going to be out watching eclipse, you should wear red or green. That would be the best of the colors. They didn't really say that.
So yeah, the question is, you should wear red or green. Those would be the best colors. All right. Having not seen this program, not entirely sure what they're referencing. So we then get into the, what is the difference between physical light and observed light? There is no single wavelength which corresponds to pink, and yet we can see pink. So that's because the human eye does not perfectly diffract light like a prism and then select individual wavelengths. The human eye has, in general, right, there are colorblind people, there are superchromats who have more. In general, we have receptors for red light, for green light, and for blue light. The red light receptors work best in the dark. The blue light receptors work best in the light, in like bright light. This is why blue light blocking glasses have become so popular, because blue light, historically, for most of human history, has only really been visible when the sun's high up in the horizon. Fun thing, right, is if you want to keep your night vision but still see, red light is better for that because the red light detectors are less, and your eyes are less sensitive to light, and so you can still see stars more easily. So my guess for wearing the red or green is because they're not blue. I was going somewhere, and then I just couldn't stick the landing. Yeah.
An hour, someone wrote about a solar eclipse that happened. At the time of that king's reign, that.
Yeah, so the question is, right, we can predict eclipses going forward arbitrarily far. We can also do that backwards. And so that's the fun thing in history, right, is how do you know when two things happened? Sometimes you've got this easy thing, right, of like, how do you know how long ago George Washington was president, right? We can say, well, we know we have a president every 4 years. We can count back the presidents. There's no broken time where we say, so there were no presidents during this era, but we promise this era is this long. Most of the time that doesn't work, right? Like, when was the last Roman emperor? That's a disputed question. What's the Roman Empire? But, right, it's a hard thing to do also just because like we've switched calendars. For most of Roman history, they didn't have summer months, right? There were only 9 months in the Roman year. That's why October 8 is 10, not 8. Right, October is the 10th month. Oct means 8. Because they just had 2 months where everyone went to go work on their farms, and so they didn't keep track of time. And then at some point, the priests would get back together and go, all right, new month. And so the way we can now like do some events, right, is one person writes, at 5 o'clock, at 3 o'clock today, it was suddenly night, and it was very concerning. And we can go, okay, we know they were in this general location. They got an eclipse at this time, so we know this event's here. And then you can do that and go like, okay, so then if they wrote 5 years ago, this happened, we know. 5 years from the eclipse was this. And so doing that a bunch of times, we thankfully tend to find that events agree with when they happened. We can then get into the controversies of all sorts of dating techniques. But yeah, so that is a way historians use them. Yeah.
Pretty much.
Mhm. Mhm. Yeah, no, so I would like to be clear, was not referencing biblical events. But right, like even, yeah, no, but like even when we go to like 80% totality here, right? Yes, it still looks normal. Shadows on trees can look really weird though. You do still see effects from less than total eclipses. But yes, this is primarily more looking at like scholarly writing or court records. Yeah. Yeah, but lunar eclipses happen more regularly, so you can do some stuff with lunar eclipse, especially if you have like, if we look at Chinese records where they kept good court documents for everything for thousands of years. If you got misaligned, you can realign yourself pretty easily looking through the historical record.
Guys from East and everything were excellent astronomers.
Mhm.
And they watched these stars and tracked them, and it was just so part of their lives.
Yeah, yeah. I have a different talk, which if La Crosse Public Library would like me to come back, would love to present sometime, on like this concept of the universal harmony. And right, the predictions they have are really good, right? Their length of the month for the moon, identical to our current measurement. Transit time for Venus, they have to within like 4 decimal places. It can be really tempting to go, oh, we can measure things way more precisely now than we could before. And that's not always true. Also, right, like we're less dedicated now than they used to be. Yeah. Mm-hmm. Right. Yeah. So the comment was more like, right, the calendar ending in 2012 was not just a laziness thing, right? Like we have calendars, they restart every January. Same concept. And yeah, I guess that might not have been clear when I said, yeah.
So besides the social aspect of watching this, feeling like I can't look at this like a sporting event, we're all doing this together, that social aspect of it. What scientific things are they testing tomorrow that maybe they don't normally can do?
Yeah, so I say unfortunately, really it's very fortunately, right? A lot of the really exciting discoveries we can make from eclipses, we've already made. Right, so one cool thing you can do with eclipses is you can test this idea of gravitational lensing. So Einstein predicts that light is affected by gravity, which feels weird, and it's not something that's predicted pre-Einstein. And during an eclipse, you can in fact see that stars, which you know where they are in the night sky, are in a different place because of the sun. Right, we detected the corona, we detected helium in the corona. They still use it a little bit to map solar flares, but much in the same way that, being a musician, right? Taylor Swift plays that big concert, and that's really exciting. She also spends hours each day practicing and rehearsing and doing all the grunt work. Much of what will happen during the eclipse is that sort of thing of like, yep, this is exactly as we predicted, this is exactly as we predicted. Right now, the big exciting thing I think with science is in biology, because, right, this is the last total solar eclipse on the continental US until 2044. Say that 10 times fast. Right, so if we're looking of like, how do swallows react to the eclipse? You can't do any sort of controlled test, right? Because we say, okay, so this swallow, like went to sleep during the total eclipse. Get to 2044, oh, that swallow is dead, and so are its great-great-grandchildren. So it's this really hard thing where we've got tons of anecdotal evidence about what happens to animals during eclipses. Some fun examples. Orb weaver spiders rebuild their webs each day. They tear their webs down during total solar eclipses. It's often observed that horses start going into their pack pattern like they do when they go to sleep. Dogs tend to go crazy, but dogs are the hard one because dogs are also very attuned to their owners and no one's normal during an eclipse. So yes, biologists really curious what happens, so constantly collecting data. That is sort of the only exciting stuff. Yeah.
You kind of jumped to my question actually, but yeah, like the 2017 eclipse, I think we were close to totality where I was, and yeah, it just got eerily quiet, and then all of a sudden you can just crazy. So I was just curious, yeah, just general effects on animals, but who's covered.
Yeah, there is not a like well-accepted scientific consensus on what happens. I will say it is, if you go somewhere rural enough that like it's the primary sounds you hear are animals, not humans, it does get weird during the eclipse. Yes, it also gets weird if you're near people because most people go silent when it first goes to totality. Yeah. Yeah, so the question is, how can you improve your chances of seeing the eclipse with weather? If you have a faster car, you can drive faster, chase the clouds away. If you plan really far ahead, right, you can go places with less clouds. Day of, no, same issue as like any day it's cloudy that you want it to be sunny. Yeah.
During the eclipse, and it says they're trying to capture information at various points in how atmospheric evolve during an active eclipse.
Oh.
And they're going to be able to actually compare this to the October eclipse from last year. So the same lights and same. I mean, they do all sorts of things out there.
Yeah. So there's a lot of things. Yeah, so right now we're at the really exciting juncture of science where about 100 years ago, not to the day, it's more like 120 years, famously a Nobel Prize winner and physicist said physics is basically done. All that's left is getting that little bit of extra precision on all our measurements. And then we discovered quantum mechanics. For many parts of science, we're at a similar phase or we're still at that phase. And so a lot of the experiments that go on during the eclipse are sort of the negative tests, right? Of like, this shouldn't make a difference, or it should be this really easy to understand difference. But we haven't measured it, so we can't say that for certain, right? I can say if the moon orbited at a different angle, eclipses would be different. And I can show you a bunch of math to prove that. But until it happens, you shouldn't be totally convinced. We then get into the whole, what is the difference between science and reality? Does science measure reality or does science model reality? Theory of science is a very fun topic. It is also a very dry topic if you don't think it's fun. Great. Any other questions? If not, thank you so much for coming.